path. So I'm going to do the same thing. It's just that reactants and products both are flowing inlet outlet is at the same temperature in this problem at 533 Kelvin. So this is a horizontal line. So you cool it from 533 to 298, carry out the reaction, heat it from 298 to 533. But in general, T inlet, T outlet need not be the same. T inlet and T exit need not be the same. But in the question I gave you, standard heat of combustion of methane, the reaction was being carried out at 533 Kelvin. Okay, so CH4 plus 2H2O oxygen going to 2H2O plus CO2, all in gaseous state. So now just find out the 3 delta H's, and you can use the CP mean table because methane is available here. Methane is available as well as oxygen data and CO2 and H2O. So in other words, you don't have to integrate. You will just take the CP mean of, say, a reactant. Okay, then you will multiply it by the stoichiometric coefficient. If it's oxygen, it's 2. And we will do that and sum it over both the reactants, sigma over the reactants, and then 533 minus 298. Okay, and you will do the same for the products. 1 minute. Okay, so that was for the reactant. Now you will do the same thing for the products. You will find NCP naught mean sigma over the 2 products. Okay, and that will be just 2 for the H2O and 2 into H2O gas, which the CP mean you will read from this, plus 1 into CO for CO2, you will again read the CP mean from this, and that's the sigma. And then you will subtract the sigma over the products minus sigma over the reactants. That whole thing you will multiply by the temperature difference delta T, which in this case is 533 minus 298. So please find the average molar heat capacities from this figure so that you know how to use them. And by the way, the x-axis is given in Fahrenheit. Okay, so you have to convert that to degrees Celsius. Okay, that is there's just no table. I couldn't find any table with degrees Celsius or Kelvin on the x-axis, but it's not a problem. Don't forget that the good thing about the y-axis is whether you do it in the foot-poundal system or you do it as calorie per gram mole per degree Celsius, the reading is the same. It just happens by chance. So in that sense, it's only the x-axis where the temperature is in Fahrenheit. So you just have to convert it. So 533 Kelvin, you have to find equivalent in Fahrenheit, and then you can read the CP mean and tell me what values you're getting. Bhavya, is my question okay? Clear? So you are you have to find the value of delta H naught at 533 Kelvin. So you're going to divide that into 3 terms. So delta H naught 533 is delta H naught at of the reactants plus delta H naught for the reaction itself at 298 plus delta H naught at the products. Okay, and delta H the products and reactants. In this case, the temperature difference is 533 minus 298. So you can club the sigma Cp mean for the products minus sigma Cp mean for the reactants all together. Put it all within brackets. Find the difference, multiply it by delta T, and then add it to the heat of the reaction. The heat of the reaction itself you have to find from the heats of formation. For oxygen, it's 0. For you have to get the CH4 delta HF from the tables, then CO2 delta HF, then H2O for vapor, okay, gas. They will be differing by the latent heat. So make sure you read the right value because otherwise it's quite a large amount. So and then multiply by 2 by the stoichiometric coefficient for the reaction given, and that will be the delta H naught at 298. So the answer for this is minus 191 kilocalories per gram mole. Kilocalories, okay, not joules. Kilocalories per gram mole. So when you read the table for methane, you have to take 533 Kelvin, convert it to Fahrenheit. That's about 500 Fahrenheit, 500 degrees Fahrenheit. At 500 degrees Fahrenheit, find what is the value of the mean Cp for methane. That's about 10 calories per gram mole per degree Celsius. Similarly for O2, which is 7.3, for CO2 9.9 and H2O 8.2. So once you have that, you can calculate the enthalpy change of the reactants cooling and the products heating to 533. 298 to 533, cooling from 533 to 298 Kelvin. Suppose there were more than one reaction, then you will find the weighted delta H naught reaction. That is, you will multiply how much extent of the reaction or what fraction reacts by reaction 1 into the delta H naught of that reaction at 298 plus the whatever fraction reacts by reaction 2, assuming they are parallel reactions, times the delta H naught for the second reaction. That's the net delta H naught 298 heat of reaction change for both the reactions.
Oh, excuse me, sir.
Yes, yes, yes.
I had a query. Like in the tables provided, we can see for the CP versus like Fahrenheit graph,
Yeah,
we can see that H2O, Cl2, O2, H2, etc. are pretty much straight lines, while CO2 is like a
yes,
curved line.
yeah, yeah.
So,
Yes,
so
yes.
what's the reason for this?
See, you see, it all has to do with the nature of the gases, you know. I mean, CO2 is a very polar molecule. It's very polar molecule, so it will behave very differently from simple non-polar gases. Okay, so this has come directly from experimental data, so they can follow. There's no the only rule we know is that Cp naught increases with temperature for all systems at a constant pressure, right? Actually, everything is given by that basic total differential. If I write H, I mean, this is not part of our course, but if I were to write dH, then I can write H as a function of P comma T, then I can find del H by del P at constant T and multiplied by dP, and to that I can add del H by del T at constant P and multiply by dt. So all of these enthalpy changes, which are also given by Cp dt, essentially, it's a depends also on the pressure variation in general, right? In general. So actually if we want to be exact, we have to use that total differential dH is equal to del H by del P dP plus del H by del T dt, etc. Right? That is how it ought to be calculated. And you have to experimentally find the partial derivative of enthalpy change with pressure at constant temperature, partial derivative of enthalpy change with temperature at constant pressure. One of them is nothing but Cp, the way you define it at Cp at constant pressure, right? That is how it's calculated. So it all depends on how that partial derivative behaves. That depends on the nature of the system. So polar gas like CO2 will not behave like the others that you named. Vishantan, is that okay?
Yes, sir.
In fact, there are so many variants of this question that we can make. For instance, I can one very popular thing would be to combine mass balance with the energy balance. I mean, instead of asking you a separate question on mass balance, since you need to know N, the stoichiometry, the number of moles reacted, that you'll have to find out from a mass balance, because in the question you just now did, you just had the stoichiometry of the reaction, but in general we said that there would be a fractional conversion, right? So it's very simple to incorporate a fractional conversion, and then first you have to do the mass balance, and that will give you the N of each reactant and product, right? For instance, if I supply excess air, nitrogen, then you know how many moles of nitrogen, like you did in the material balance, which by the way, everybody did very nicely in the exams. So almost full marks for all. So that was quite good. Right? We should have done absolute grading, you know. Just imagine everybody. But the thing is that committee is going to kill me. That's all. I mean, anyway, that's hardly a Incidentally, I had one more interesting. Today, I wrote an email to your convener, right, Devapriya, and then I just wanted to. I refrained from doing it. Then I said, well, should I address it Devapriya or Priya Dev? But I refrained from doing it. I hope. DP, is that a good one or it's a poor one?
Yes, sir.
It's a poor one, no?
No, sir. It's a good.
So I almost had it, but then I said no. I still don't know any of you really. It's only online, and everybody is just an abbreviated symbol. So I refrained from doing that. So what you can do instead of so here we said Q equal to delta H. Now very often, if I ask you what is the maximum temperature that can be reached by combustion of methane with excess air, the maximum temperature, when will that be reached? It'll be reached when you put that delta H term equal to 0. Okay. So for instance, the same problem becomes a little more interesting. In fact, that is exactly what I wanted to. That is what. So you can take this. This may be a more useful problem because it's more relevant. I mean, normally the combustion will have excess, no? That's what we did before, right? So first you have to do the mass balance. You have to write the equation, the same equation, complete combustion of methane with oxygen, going to CO2 plus 2H2O, 1 CH4 plus 2A2 going to CO2 plus 2H2O. The delta H naught 298 of this reaction is about minus 191 kilocalories. Okay. That is what you will find from the heats of formation if you were to do that. That's a separate table you have to consult, okay, from books. Now, the question is, when will you get the maximum temperature? So for the maximum temperature, you have to take, so we had taken Q is equal to delta H, but when you have adiabatic conditions, when the process is taken to be adiabatic, then only you will get the maximum or the so-called flame temperature. Okay, so that means Q is 0. So since Q is delta H for our flow system, and there is no shaft work, so W subscript S is 0, and Ke and P potential energy, kinetic energy changes are negligible. So Q is delta H, and since Q is adiabatic, the process is assumed adiabatic, so delta H is 0. So now you are going to calculate the delta H, which means all the three terms, right? So you have to take the final temperature to be T and frame the equations for those three terms. You have to cool the reactants from T to unknown T to 298 Kelvin, then carry out the reaction. I just gave you the enthalpy change, but you have to find the material balance because everything is not, there will be excess oxygen, excess nitrogen entering, right, along with the air. So you have to find out what are the gases that are leaving the burner, what all they will contain. Uska composition निकालना होगा by mass balance. So first find if I burn 1 gram mole of methane, that's our basis. Then how many moles are required? 2 as per the reaction. So find out the excess moles of excess oxygen that are there, and along with that how much nitrogen comes in, and then find out in the product at temperature T final what is your composition of the gases leaving the burner. Then formulate the equation for delta H with the three terms, put all of that with these material balance N's for CH4, CO2, H2O, gas, oxygen, nitrogen, and put that equal to 0 to get the flame temperature or the maximum temperature under adiabatic situation. And again, you can use the graph that is shared with you. Of course, it can be done by integration, but then it's not a linearized problem because then you will have T cubed polynomial terms. So you have to do by iteration then. But the good thing is these gases are all there in the graph that we shared with you. So you can use that for the average. And so first find out how many moles of reactants are there, that is at 1 atmosphere and 25 degrees Celsius. Entering at 25 degrees Celsius, right? And then it's heated to some temperature T final. So at 25 degrees, the limiting reactant is CH4. Find out how many, what is the composition of the reactant. So of oxygen and 0. moles extra of excess oxygen. So 2.4 moles of oxygen, and along with that you'll have 80 by 20 into the 2.4. So that's around 9, more than 9 moles of nitrogen. That's your reactant. Now formulate what is in the products at 1 atmosphere and the final temperature capital T. So what is the composition of the product stream at temperature T and 1 atmosphere? How many moles CO2 does it have?
So since we started with 1 mole of methane, so we'll have
Yeah,
1 mole of
1
CO2.
mole. How many moles H2O?
2 moles of H2O.
Very good. How many of the nitrogen and how many of the oxygen?
So oxygen, since it was 20% excess air, so it'll be 0.4 moles.
Correct. Because the 2 moles have reacted, so what is not reacted is 0.4 moles of oxygen. And then how much of the nitrogen?
So can we take the nitrogen to be like 8 moles, because 7.9 approximately.
Yeah,
Right?
80 by 20. You can take it 80 by 20.
Yeah, so that'll be 9.6 moles of nitrogen.
Right. So this is your composition. So these are the ends you have to use with the CP means. But now your problem is you don't know the CP, you don't know the final temperature. So the delta H, see what is the enthalpy change of the reactants here? Delta H, not R, what we call in our diagram. 0, because it's entering at 25 degrees Celsius and our basis reference state is 25 degrees Celsius. So there is, because you don't have to cool anything to 25 degrees because you're entering at 25 degrees, right? So that enthalpy change is 0. Okay, now delta H naught you're carrying out of the reaction, and that you will find out from the heats of formation. That's about minus 191 degrees. That's the heat of reaction that you can check with the heats of formation of those 4 components. Oxygen is 0, and just do that and get minus 190 minus 191 kilocalories. Now, what about the enthalpy change of the products at standard state? Suppose T is the final temperature in Celsius. The delta T is T minus 25. The number of moles you just now told me. CP mean of each product times N times T minus 25 and sigma over all products, right? That's the enthalpy change for the products. Sigma over products of NCP not mean multiplied by capital T minus 25 degrees Celsius. So now that's the net enthalpy change, and for adiabatic conditions, we said that that is 0. So what you are going to get is that minus 191 kilocalories plus sigma over products NCP mean T minus 25 is 0. So you have to solve this equation for the unknown temperature. So this is a simple, it is a case of a combined mass and energy balance, of course, for one reaction, but even if there are multiple reactions, there's nothing to get afraid of. If there's a side reaction, we will find, okay, what is that side reaction? It will be told to you what it is. So you will see methane plus water giving you, let us CO plus H2, right? It's something else, and that uska bhi enthalpy change आप standard condition में निकाल सकते हैं, because you know what the components are from the heats of formation. Only you have to know the extent which reacted by first the main reaction and then extent which reacted by the side reaction, and the and for the reactants products it will be the same cooling heating. You have to do the mass balance and then do the energy balance. And if you have the CP mean data in that in those graphs, it makes it easy. Otherwise, you have to integrate CP dt and find alpha, beta, gamma, delta, etc. from the tables. So the answer for this question is 1765 degrees Celsius. 1765 degrees Celsius. So you can just check with the graph that you have, work it out so that you get some practice. DP, you are all going to go for mid-sem break soon, right?
Yes, sir, on 29th.
Yeah, I mean, go means what? You are going to. I think it's actually not really meant for you. It's meant for the final year students so that they can have their placements. Correct?
I
I mean,
have no idea, sir.
I think that's why this gap is given, right? Because the final year people they start their placements from 1st December. It's always starts 1st December. By 15th, it's finished. So that's why I think this break has been given. Otherwise, why should the break be given? Anyway, so what you have to do is you're going to have groups of 6 with one group leader. And DP, you will coordinate that. I mean, each you first do it for your. Let everybody else come up with the group leader for their group. And if they can give it to you, so there'll be around what, 12 groups then?
Yes, sir.
Yes, sir. 11 to 12.
12, 11 to 12. So very good. So we will, so you can take anything, and 27th, you can make a 12, 13-minute presentation. Let us start based on alphabetical order of the first name of the group leader. So you know what order you're going to do because you know the group leader of each of those 11 teams. And so we have only 3 classes after that. This time it's a shortened semester, you know. And then you can start from the first name, whoever is the group leader, whoever has first name, we can go alphabetically till it's finished by January 3rd. We'll have 3 classes for that. Okay, DP, you can coordinate that, right? So that 27th,
Yes, sir.
we'll have to start with the presentations. So just see how the groups, because either whether you want to all 6 have go together and they will be doing, or each one will do separately for a couple minutes. You have to it can be different. Okay, I'm not imposing any. It can be done as you please, but we have to all do it online. So when we meet 27th, we have to very soon start on that. So as I said, I'm on leave from 1st December. So I'll only be back on the 25th evening. But it's fine. I mean, I think 27th is going to be our first class.
Sir.
Yeah.
Sir, do we have a class on Saturday?
Not. Do we have anything now? I think we are done with
Yes, sir.
everything. Why don't you make the groups that needed to be done earlier? It never could be done. If you can make the groups, then just the leaders of those 12 groups, Devpriya can just send me by mail, and so you know the alphabetical order. इतना वो भी तो आपको करना ही है. Actually, the thing is, I have a very good memory for people, names, everything, but this time I haven't even seen any of you. So generally, I take a lot of interest in, I mean, remembering. I mean, I don't have to do much effort to put to be honest, but so you need to, I don't know all the names also. But maybe I'll get a chance again to, if I continue fluid solid system. That's, I don't know, because I haven't done it. I didn't do it last year or the year before that. This time it's assigned to me, so I'll teach probably your senior batch. I don't know them either. I haven't taught them, so it'll be a first time, I think. So that's fine. I mean, you can make the groups. Either way, be ready 27th. Because we cannot, everybody we have to give the same amount of time, say 12 minutes or so, I mean. And then the majors are just on us very fast. But I think we have covered that thing. So on these lines, you can actually work out any problem for which you know the reaction and you know the extent by, even if multiple reactions. The mass balance part we have already done, spent a lot of time, so there's nothing new to be done. You have to know the number of moles of every reactant and every product. Okay, like here you just calculated and you told me what they are. And then the energy balance is also fairly general. It will have those three terms, and it's just a little more calculation, but otherwise the procedure is the same for every problem. You'll be able to find the, of course, I'm assuming it's a flow process. Don't forget that when we use the unreactive balance, normally it was not a flow process, it was a closed system. So Q was equal to delta U there. Here Q is, we are taking delta H because the reactants are flowing in at some rate, just as in the mass balance equations that we solved for in a steady state flow process. So that's what we have taken here. That's why you put delta H equal to 0 for the maximum. Okay, but in the non-reactive thing, normally for the closed steam packet, we took Q is equal to delta U. So that's okay. But if there it was a flow, you would take Q equal to delta H, right? So I think that's more or less, we are towards the end. It's the semester has gone very fast. I mean, compared to every other semester, I must say. Are you all right? Otherwise, what do you
Yes.
plan to do in these you know, midsem break, so-called break? What are you gonna do? You're all going to be at home, I guess.
Yes.
So will it be any different, or?
So I guess we can't say as of now.
You will stay at home and just, you know, do a little bit of revision for your courses, plus do some other hobbies or something.
Yes, sir.
Yes, sir.
Okay. So very well. I hope the first couple class, you know, there was some problem with audibility, all that we settled. So after that, it has been fair, you know, except that I can't see you all. That's all. Anything else? Is it okay?
Yes, sir.
All right. So then have a very nice break. 15 days. It's 2 weeks long break this time. Normally they just give you 1 week and 2 weekends. So you have full 2 weeks, I think. Enjoy. And I'll see you now on the 27th. Okay. Thank you.
Thank you, sir.
Devpriya, thank you
Thank you,
also
sir.
for, thank you also for all the interaction. DP. All right. Good luck here.
Thank you, sir.
Yeah, welcome,
सर
welcome. Enjoyed it. Yeah.
सर सैटरडे को थर्सडे का टाइम टेबल है तो उस दिन आपकी क्लास होगी
आप बताओ अगर आप चाहते हो तो, if you want.
सर बट लाइक इफ द सिलेबस हैज बीन कंप्लीटेड तो अभी मैंने एक
I
गूगल डॉक शेयर कर दिया है एंड एवरीवन इज एंटरिंग देयर ग्रुप्स इन दैट सो आई विल फॉरवर्ड इट टू यू
that if you can do that, that is also part of the assignment, because that has to be done. It has
Yes.
20%. We have to. Yeah. Okay. All right. Itna kar lo aap.
So,
We'll meet on
and so
27th.
just one more thing. So if
Yeah.
we have any doubts in our presentation, so can we like email to you when you are on vacation, 1 to 25 December?
You can email me till first.
Okay, sir.
After that, yeah, can't say. I mean, eh, if you want, you can email me after. I'm back 25th night. 26th, if you want, you can.
Okay, sir. Thank you.
Yeah. I mean, it's basically I there are other commitments for me this time. It's COVID time, and we have to solemnize some occasions. So, so I don't know if I. Yeah, you can mail me on 26 if there is something. Okay. All right.
Okay,
Good
sir.
luck then. Yeah, lovely.
Thank you, sir.
Yeah, lovely.